October-November 2022, Paper 4, Variant 2. Question 1. Calcium chloride is an ionic solid, and the table 1.1 gave a lot of enthalpy. So we need to use this for the calculations later. Let's move on to the part A. Define lattice energy. Enthalpy change when 1 mole of ionic compound or ionic solid is formed from gaseous ion or from its gaseous ion. Let's use this example. If let's say we want to know the lattice energy of calcium chloride, so we need to use the gaseous ion. So the gaseous ion that form the calcium chloride is the calcium ion, gaseous form, and the chloride, gaseous form. And these two gaseous ions, they react and combine, then it will form this solid calcium chloride. And this one must be 1 mole. 1 mole of the solids form from its gaseous ion. So this is a very easy definition that you must know. Okay, so now for the part B, this is a calculation. So it's want to calculate the formation of calcium chloride. So this question is to calculate standard enthalpy change of formation of calcium chloride. So the starting point is important. You must know where to start. And most of you should recall what you learned in AS, the enthalpy change of formation. For the enthalpy change of formation, we know that it must be 1 mole of compound form, in this case is the calcium chloride, from its elements. The elements that involve, it must be calcium and chlorine. When these two elements react and form 1 mole of the compound, so we say that this is the enthalpy change of formation, which means when you start to calculate this and draw the energy cycle, you must start with this one. You have to construct the equation for the formation. So second step is you need to link these reactants and products together. The one that you can use to link these two obviously is the gaseous ions itself, because the element means the calcium and the chlorine, they can ionize and form gaseous ion here, and these gaseous ion can form the solids. So therefore the gaseous ion is the only thing that can link these two together now, which need to use for the calculations later. So if you understand how the thing works and how they relate together, then we can start the calculation. Because the main purpose for this question is means part B is to find this formation. So therefore we need to get the enthalpies, the sum of enthalpies in this part and the lattice energy. So let's start with this part, calcium and the chlorine. Calcium need to undergo atomization before it forms ions. So therefore 193 is the atomization of the calcium, means from the solids to form gas. After that, the gaseous atom will undergo ionization, and it needs to release or remove 2 electrons. So this is the first ionization energy, and this is the second ionization energy. So this part, this 3 is for the calcium to form the calcium ions, and this one is the enthalpies for the chlorines to form chloride. So because we know that 2 chlorides need to be formed, therefore it need to use 2 atomization energy. So this one 1 to 1 is the atomization energy, enthalpy for this chlorine, and because it need to form 2 moles, so need to times 2. Then the 2 moles of gaseous atom now need to get the electrons, so the EA here need to times 2 also. So this is the atomization energy for the chlorine, and this is the EA, electron affinity of the chlorine. So both times 2. Okay, after that, you need to use the lattice energy. The lattice energy for calcium chloride is given, is negative 2237. Okay, so once you get all these this energy or enthalpy, so you can perform the calculation. So we know that this is the energy cycle. This enthalpy plus this enthalpy, so is equal to this enthalpy. So therefore we have this calculation. So delta HF, now therefore we know that is the sum of the first pack of energy and the second pack of energy. Alright, so this one is the sum of these two. So eventually you get negative 790 kilojoule per mole. So this is how you calculate the delta H formation for the calcium chloride. And of course you can get all these values from the table. Okay, it's given all here. Part C. 3 possible values for the first EA of bromine are shown in table 1.2. Only one is correct, or one of them is correct. So choose the answer and explain. So first, you need to use the values in the table 1.1 and compare. Electron affinity of chlorine is negative 364, and need to compare with these values, these 3. Okay, then you need to know the difference between the chlorines and the bromine. So chlorine, the size is smaller than bromine. Okay, bromine, because size is larger, so the nuclear attraction is weaker. Weaker to what? Weaker to the incoming electron. Because in order to gain electron, the nuclear attraction is important, because it will try to attract the incoming electrons. So we know that the size of bromine is larger, the nuclear attraction is weaker due to the shielding effect. So therefore, the ability to gain the electrons, the incoming electrons, is weaker, and therefore the energies that release is lesser because the bond is weaker. So that's why we know that the chlorine, when it gains electron, the bonds that form is stronger and it's released more energy, so it's more exo. And the bromine, because the attractions is weaker to the electron, the bonds that form is weaker, release less energy, so it's less exo. That's the reason why we should choose the first one, because the first one is less exo than the EA of chlorine. So we choose this one, then explain. Just explain using the size. Bromine atom has a larger atomic radius, therefore weaker nuclear attraction to the incoming electrons. It means the electrons from outside. Part D. The enthalpy change of hydrations of chloride ion can be calculated using the lattice energy of the calcium chloride and this data in table 1.3. So this one you need to know how to use the energy cycles between the gaseous ions and the aqueous and the solid. Okay, later we will come to this definition. So let's look at this energy cycle first. We know that gaseous ion, they can combine and form the solid. So the enthalpies involved is the lattice energy, gaseous ion. And we know that the gaseous ions actually it can dissolve in the water. So to form the solution means the enthalpy is the hydration's enthalpy. And of course at the same time, the solids that form also can dissolve in water and form the same solution. And the enthalpies involved is the these solutions, enthalpy change of solutions. Okay, so therefore we have this relation, means delta H LATT means the lattice energy plus the enthalpy change of solution is equal to the enthalpy change of hydration. So that's why we have this relation, this one. So hydration enthalpy is always equal to this lattice energy plus the enthalpy change of solution. This is how we get this relation, right, from this energy cycle. Okay, so now before we move on to the calculation, let's look at the definition. And these two definition is very easy and it's quite similar. Define the following terms enthalpy change of solution. So it's an enthalpy change when 1 mole of ionic solid or ionic compound dissolve in sufficient water to form a very dilute solution. So the key is what? The key is must be 1 mole of ionic solids and water must be sufficient. Why? Because we want to make sure all the ionic compounds dissolves. So that's why what the amount of water must be sufficient. Okay, second definition is this enthalpy change of hydration. So it's enthalpy change when 1 mole of gaseous ions dissolve in sufficient water to form a very dilute solution. Now it's still 1 mole, but hydration is always the gaseous ion. So it's 1 mole of gaseous ion dissolved. It must be sufficient amount of water as well. Means the hydration here, this one, it must be the gaseous ion dissolved in large amount of water to form the solution, right? And remember, the enthalpy change of hydration for this calcium chloride, this calcium ion and chloride is actually the sum of 2 hydration enthalpy. So it's the hydration enthalpies of calcium ion plus 2 times of hydration enthalpies of chloride. So when we sum up these 2 hydration enthalpy, then it's the sum of the hydration's enthalpy for this reaction. Okay, now part 2. This is a calculations, and first you must use this equation, and this one I already discussed just now, how we get this. So now the lattice energy is already given in the table, negative 2237. Delta H solution also given, negative 83. Please refer back to this table. It's not here. Negative, it's not this table. It's this table. Sorry. Okay. It's here. This table, negative 83. So use this one and substitute to this. And this is the part that you must be careful. Delta H hydration, I told you just now, is the sum of the hydration enthalpy of the cations and the anion. So therefore, you must use the hydration enthalpies that given in this table the hydration enthalpy for this calcium ion, negative 1650. Okay, substitute to this, and plus 2 times of hydration enthalpies of chloride. This is what we need to find. So remember, it must be 2 times, because in this cycle, as you can see, it's involved 2 moles here. So it must be times 2. Okay, after that, you just need to rearrange. Then you can get the hydration enthalpies for chloride, which is negative 335. Part E. Calcium fluoride can be synthesized direct from its elements. Okay, this is equation. Calcium fluoride solids form from its elements calcium solid and fluorine gas. It must be 1 mole. The value for the delta HF for this calcium fluoride is negative 1214 kilojoule per mole. Okay, first part, predict the sign of the entropy change for this synthesis. Explain your answer. Okay, this one you have to compare especially the state. Before the reaction is solid and gas. After reaction is just solid. So we know that the gas has a higher entropy. So when these two reacts, it just forms solid, means the entropy is decreasing. So when the entropy is decreasing, and therefore the sign, it must be negative, because now it's less random or less disorder, because now no more gas. So therefore what you need to say is the sign is negative. Explanation is just you need to mention because there is a reduction in the numbers of gas molecule, because it's now the gas molecules is no more after reaction. Part 2. The value of delta HF for this calcium fluoride given in the E, and your answer to E1 to predict how the feasibility for the synthesis will change when temperature increase. This one you need to use this Gibbs equation. Delta G equal to delta H minus T delta S. You must put this first. After that, use it. From the part 1, because we know that the delta S is negative, so means this one is negative. So when this is negative and temperature increase, so means the T delta S itself, only this T delta S itself, it's going to be more negative. When it's more negative means when we want to minus a more negative terms, then it will become more positive, because negative, negative, positive. So means the negative T delta S, it will be, this whole terms, it will be more positive. It will be more positive. So therefore, when delta H combined with this term, means delta H minus T delta S, because T delta S is now more positive, more negative, and the negative T delta S is more positive, therefore delta G eventually will be more positive. So this is the relation, and when delta G is more positive means the reaction is less feasible. Okay, again, you can actually discuss in 2 ways. Either you use T delta S or this whole thing, negative T delta S. When you use T delta S, then you need to say it's become more negative. Therefore, when the delta H minus this T delta S, then the delta G will be more positive. Or you can mention this whole thing means you put negative T delta S. So you say that when temperature increases, negative T delta S become more positive. So therefore, when delta H combined with negative T delta S, delta G is more positive. So it's less feasible. Okay, it's actually similar way. It just depends on how you explain. Okay, so that's all. I hope you understand. Thank you.